So having covered the introduction part and explaining in detail what p-values mean and what they don't mean, let's go to the main parts of this talk and start speaking about different statistical tests and when to use them. OK, so before that, I will just mention briefly about Python and statistics. Again, I will illustrate everything, but keep in mind we have two main packages in Python that deal with this topic. We have SciPy, which is mainly for more simple kind of statistical calculations, and that's the package which you have been mostly using up until now. And then we also have stats models, which we will also see, which covers more kind of complex models. And again, we'll illustrate that. And these two packages together, SciPy and stats models, I think provide Python with quite decent statistical capabilities. And like any other package, don't forget to cite them if you find them useful. Again, the work is really dependent on the credit that we give them. I will say that despite all of these nice capabilities, Python is still, if some of you are used to working with R, I will say that it's still not as rich as R when it comes to statistical analysis. So when it comes to more kind of very advanced models and very sophisticated tests, we still, I think Python still has some progress to make, and there are still some shortcomings. But I think really the main parts are covered pretty well in Python. And for those tests which are not covered, there is a nice feature in Python which allows you to wrap R packages quite simply. So you can invoke R functions from within Python. So if you come to the situation, again, I don't think it's very likely because these are really more sophisticated tests. But if you come to the situation where you need to work with something which is not implemented in Python, typically there is a very simple way to invoke this from within Python. So for example, in R, it's very simple, and you can do that as well. Yeah. What is not covered in Python? I don't have very simple examples. Again, these are very kind of more sophisticated things. There are all kinds of post hoc analysis tests, which are more sophisticated, which I think some of them are not in Python. Some confidence intervals for very specific kinds of parameters might not be implemented. And of course, if you have very specific package, like if there is, for example, I don't know, a package for running genomic association studies. This package might be just in another language, and then you need to invoke it from within Python. Yeah. But again, I think really the most dominant and the thing you're likely to encounter, you don't need to worry about this issue too much because you do have it in Python already implemented. OK, so the plan for the rest of this lesson will be we'll go over the most common statistical tests, and we're going to demonstrate them in Python. And we're mostly going to focus on association tests, which are, of course, the most common kinds of tests which we typically use. And they're also very straightforward in this formalization of the null hypothesis, because you can very straightforwardly define it as simply the lack of association. So if we do association test, the null hypothesis would be that there is independence of the variables that we want to test. And for each test, we're also going to pay close attention to all the assumptions, the explicit and implicit assumptions that they make. And I really want you to pay attention to that detail. And always keep it in mind when you decide which test is appropriate to use. Then really keep in mind what assumptions these tests make and whether these assumptions you think are justified in your case. OK, so to choose the right statistical test, there are many considerations. But I think the most important criterion for choosing the right test is simply the types of your variables. And like we saw with visualization, that this was the main criterion for choosing what kind of graph you want to show, the same goes for statistical analysis. And again, we distinguish between two main parts of variables. So we have numerical variables, which are things which get some numeric value. Again, it can be discrete or continuous, it doesn't matter, but as long as you have some sense of which is higher and which is lower, then most probably you're in the numeric category. So it can be things like gene expression, which you can quantify. It can be temperature or number of siblings. And again, even so, number of offsprings, for example, it's a discrete. It cannot get any continuous value. It gets only integers. Even though it's discrete, it still falls most of the time into the numeric category because it's something you count. It's something that is numeric, and you have a sense of more or less. And then typically, you will want to model it in a numeric way and not in a categoric way. With categorical variables, we have things which we don't really have a sense of ordering of which is higher and which is lower. We just have different categories that we want to compare. So it can be things like tissue type. And of course, you cannot say that neurons are more than fibroblasts. It's just different kinds of tissues and just different categories. Or you have cell cycle phases, or you have some codons, which again, it doesn't really make sense to compare them in a quantitative way most of the time. And then you have some cases in which you can decide to model it in different ways. So for example, if you deal with a day of week, you may want to think about a day of week as, I don't know, Sunday through Saturday or Monday through Sunday and model it through a number. Or you can just decide that it's 7 different categories that you want to consider each on its own. And I think that the main consideration to choose this, to model it this way or the other way, would be whether you think there is some trend that you expect to be had with respect to the ordering of the days of the week. So if you expect something to start low at the beginning of the week and then to become high by the end of the week, then it might make more sense to use numeric modeling. But if you don't expect any trend, you say, OK, maybe just we have something which happens on Mondays and Wednesdays and Thursdays, and is different on the other days of the week, and I don't really know which way it should go, then most probably you just want to model it in a categoric way and just treat it as different categories. OK? OK. And then, like I said, I think maybe the second most important criterion for choosing the right test is the kind of assumptions that they make. And like I said, they make many implicit additional assumptions on top of all the explicit assumptions. For example, many tests will assume some kind of normal distribution, which is sometimes appropriate to assume. Sometimes it's less appropriate, and you need to keep this in mind. And these kinds of assumptions are really very commonly neglected, and I think it's important not to neglect them. At the very least, if you have them, then just try to keep them in mind and make sure that later when you try to interpret the results, then keep in mind all the assumptions that the tests have made and try to think whether they might have been broken. One particular assumption, which is pretty much common to all statistical tests, and I'm not going to say it all the time over and over again, that's the assumption of what is called IID. So you assume that your samples or data points are independent and identically distributed. OK, that means that if you take few samples which are dependent with one another, for example, if you want to see some phenomena and you take, I don't know, you take 2 siblings or you take 1 person and then quantify that person across several time steps, then it might be a real problem to then arrive at conclusions to the general population if you have this kind of redundancy or oversampling, or if you break this assumption of independency of your samples. So that's a very common assumption that you need to keep in mind. And of course, they also need to be identically distributed. So you need all of your samples to be from the same distribution that you then want to make inference about. So if you have different samples from, say, different populations, which are biased in some way to specific populations, then you cannot have a conclusion which still applies to a different population than what your samples are. OK, so this is a very common assumption that we won't always speak about explicitly. OK, So according to the type of variables, we break it into three main types of statistical tests. We're going to speak about numeric versus numeric variables. We're going to speak about numeric versus categorical, and then categorical versus categorical. OK, so let's begin with the case of two numeric variables. So for example, let's say we want to see whether the genome length of viruses is associated with their physical size. So we have viruses, which are the samples that we have, and then we have two variables, which are the genome length and physical size. And you can see that both of these variables are numeric. And we might, for example, expect that larger viruses will have bigger genomes. It makes sense. So the simplest kind of test that we can use is the Pearson's correlation, which you have already used. So let's go through the summary of this test and see what it does. So the input of Pearson's correlation will be two numeric variables. And the purpose would be to test whether we have linear correlation between these two variables. And the null hypothesis in this case would simply be that the two variables are linearly uncorrelated. And some additional important assumptions that this test makes is what is called normal distribution. Specifically, it assumes bivariate normal distribution. But again, there are many results that see that in reality it's quite robust to this assumption. So unless you have something which really, really strongly deviates from normal distribution, most of the time it should be all right. But there are some important limitations of this test. So one thing is, like is explicitly written here, it deals only with linear correlation, OK? So it won't deal with more general types of correlation. And it deals only with two variables, OK? So just if you have more variables, again, you cannot really use Pearson correlation. Now, if you want to use it in Python, you simply use the scipystats Pearson R function, which gets x and y values, which are some arrays or list or anything of the same size. And Python will assume that every entry within the x array will correspond to some to the corresponding entry in the y array. Okay, so in reality, you can think about it as just one set of data points, which you simply split according to the two coordinates. So let's try to see an intuitive illustration of how Pearson's correlation works. And let's speak about the Pearson's correlation coefficient, which is called R most of the time. So this correlation coefficient is a number between -1, which means full negative correlation, through 0, which would mean no correlation, all the way to +1, which means full positive correlation. And you can see some examples here. So you can see some perfect linear correlation. And then you can see that if you start adding noise to it, you still have some positive trend, but then it weakens, and you get a lower correlation until you have just only noise and no signal at all. And then you see no correlation whatsoever between the x to the y-axis. And then you get a coefficient of 0. And likewise, if you have a negative slope, you can see that you will have negative numbers. Now, it's important to state that the Pearson's correlation doesn't really care about the slope of the trend. It only cares if it's positive or negative. So as long as you have a positive trend, it doesn't matter how slopey it is, you get a positive number, +1. And then if you have a negative slope, you'll get -1. OK, and it doesn't matter what is the slope. And like you see here, there are many kinds of correlations or associations between variables that are simply not linear. So even though you have clear dependence in those cases, so you can see that in all of those cases, all of those shapes, clearly you have some dependence between the x to the y. It's not just random points. You have very clear trends that you can see here. It just doesn't happen to be a linear correlation, and as a result, you still get 0. And Pearson's correlation will not discover it. OK, so like we said, we can use SciPy's implementation, which will give you an R coefficient and a p-value as a tuple. And like I said, it assumes a normal distribution. Yeah, okay, so, but yeah, as long as you have a large data set, even if this assumption is not met, most of the time it will be okay. But in some rare cases where it doesn't hold, there are some other alternatives. For example, you can use a permutation test, and we're going to speak about it later. Okay, before we move on, any questions? Okay, so let's say that we run Pearson correlation, and we see some correlation in our data sets. We can then ask the question whether we can predict y values given x. And for that, we need to use a slightly different tool, which is highly related to Pearson's correlation, but is somewhat different, which is called linear regression. And again, I assume that all of you have seen linear regression models, those nice trend lines that you see here. So given some data, we may want to fit into it some trend, like you see here, some line that we think best fits into the model and best explains y as a function of x. So for example, given this data, we can come to the formula of this line that is, we expect y to be roughly 0.2 times x plus 5. And that's the line we see here. So let's try to give a little bit of mathematical intuition and background about what these regression lines mean and how they come about. So the way they are built is through the process of trying to minimize what is most commonly used, the mean squared error, or in short, MSE, which is the formula that you see here. So for every point, like in this illustration that you see on the right, you see 6 different points. So we define by yi to be the real y value of each data point I. So this would be the blue values, at least they're y values. And then you have the predictions that you try to make, that your model makes, which are simply the projection of those points on the line. So simply taking the x value of each point and projecting it to the line, which is what you see here. And then the difference between them, so we define those as yi hat. So the difference between yi and yi hat, which we denote by ei, is typically called the residual, which is simply the error between the real value and the value you predict, which is what you see here is the green sections. So they measure the residuals. And then the mean squared error, the MSE, is simply the average of the square of those residuals. So we take each of them, we square them, and then we take the mean. And that is a very commonly used metric of how well we manage to fit this line into these data points. So if we combine these two notions together, we want to use the MSE objective with the linear regression framework. We get what is called an ordinary least squares, OLS for short, which is the most typical and standard kind of regression analysis we can use. And then from this, we get another measure, which is called the R squared. Here you can see this is a capital R, unlike the Pearson's correlation, which was a lowercase r. So when we use MSE objective, then we can calculate from it what is called the coefficient of determination, which is this R squared. And that's defined as 1 minus the MSE over the variance of the data. Now the formula for MSE we've already seen. To remind you, the variance, you can see it's a very similar formula, but here for each point, instead of taking its prediction, we take a constant point for each of them, and which is simply the mean, which we denote by y bar. And then we get the square distance between the points to the mean. And again, we take the average of these, and this defines the variance. So to give an intuitive explanation of what this number means, again, you can see the formula here on the bottom. So when we have that the mean squared error is 0, you can put it into this formula and get that you get an r squared of 1. And that means that you have a perfect fit, because you have no error at all. Your line fits perfectly, and for every point you have a 0 residual. You get that the prediction fully matches the true value. So that's the maximum you can aspire to a value of 1. But on the other hand, if you get that the mean squared error is the variance, again, you can put it into the formula and see that you get an r squared of 0, meaning that you get 0 information. So x gives you no information whatsoever about y. So if you just guess the same point, if you just guess the mean for each point, you just get the variance, which is the same error that you get if you use x. Okay? So that's theoretically like the lowest you can get. Of course, in reality, you can always create a model which is even worse than random and get lower values. But in these cases, of course, you shouldn't. It's not something you should do. So if you use proper algorithms, the lowest value you can possibly get would be 0. And then in the end, you get some measure between 0 and 1, which tells you, you can think about it in an intuitive way, what fraction of the variance of y is explained by x. And that's really, if you look at this formula, that's really what is explained here. You can see the fraction of the variance of the mean squared error, and then you get the complement of that, which is what fraction of the variance is explained by x. Okay, so the MSE over the variance will be the fraction of the variance which is not explained by x, and then the r squared will be the fraction of the variance that is explained by x. And that, I think, is a very intuitive definition that people very often use. And I think it's important to know that. And you can also see it in many other domains that people sometimes use it. So for example, when you see people like measuring the heritability of certain traits, saying, for example, I don't know, that height is like 70% heritable, typically what they mean is that the r squared is 0.7, meaning that 70% of the variance of height in the population is explained by genetics. And then you can see simple saying things like, if you use some, I don't know, polygenic risk score, you can explain like 40% of the heritability, which again means that you get this coefficient of 0.4, which is only 40% of the heritable component that you can explain by this model. Any questions?
What's the relationship between Pearson's R and the R squared? Is it?
Yeah. OK, that's the definition of an excellent question, because we have a slide on that. So yeah, they're very tightly related. So in the case of OLS, they indeed coincide. So if you take the Pearson's correlation R and you take the square of that, you will get the same number as you get from the linear regression. But it's important to state that that's only in the case of OLS. If you use different kind of regression models, if you use different kinds of objectives, or anything different, then this no longer holds, and you get a different measure. Okay, but in this particular case, they are the same, and it's a very, indeed, very convenient way. So it essentially gives you a different way to look at the same thing. Yeah. So for Pearson's, we just get a p-value and a coefficient, and the linear regression will give us a concrete model. So it's a bit richer, but again, different ways to look at the same thing. Any other questions? OK. So if you want to run linear regression, you can use the stats models API OLS function. OK, so notice that here we use the stats models package, which will give you a standard regression model. And yeah, like I said, we have many different kinds of more advanced models. For example, you have robust linear models, which are less affected by outliers. So OLS is very, very sensitive to outliers, like we're going to see. And soon I will illustrate it with Python, and we can see some concrete examples. But before that, let's ask the question, what happens if we have some correlation that is not linear? Like we said, Pearson correlation deals only with linear correlations, but many times we have something which we have no reason to assume that is linear. Like you see here, you can see that in some sense we have perfect correlation here because x and y really go together. So the higher x becomes, also y grows. So they really go together, but it just doesn't happen to be linear. And as a result, even though it's a perfect nonlinear correlation, we only get some correlation with Pearson's. We get a high correlation of 0.88, but it doesn't reflect the fact that we really have some perfect correlation here, and we might expect to get 1 in this case. So for that, we can use what is called the Spearman's rank correlation, which works very similarly to how Pearson's correlation works. Again, it gets 2 numeric variables, and what it does, it tests whether those 2 numeric, whether you have some monotonic correlation between those 2 variables. And here the null hypothesis would be that the rank of these 2 variables are uncorrelated. I'm going to explain what rank means exactly in a bit. And the nice thing about it is that it doesn't make any assumptions whatsoever. Okay, so that's what is called a non-parametric test, a statistical test which doesn't make any assumptions about the distribution of the data. And as a result, it's applicable to any distribution. Okay, so these are non-parametric tests, and we're going to see some examples of them. So they're very strong in this sense. But still, it does have some limitations. So again, it deals only with monotonic correlations. So you can have some kinds of more strange associations which are not even monotonic. So for example, you can think about a parabola in space. So for some values it's high, and for some values it's low, and it doesn't go in a deterministic way. And again, we deal only with 2 variables. And the implementation you can see here, again, you use SciPy stats package, and then you have the Spearman R function, which works like the Pearson's function. Now, I said that this test is based on the ranking of the values, so let's try to explain what exactly it means. So let's say that we have just 4 data points with the following x and y values that you see here. Then the ranking is simply to order these numbers from lowest to highest. So in the case of x, we see that the ranking is 4, 2, 1, 3, meaning that the first value, 5.2, is the highest, so it gets 4. The second, 2.1, is the second lowest, so it gets 2. Minus 3 is the lowest, so it gets 1. And 4.2 is the second highest, so it gets 3. And likewise, we have for y, we can get the ranking of y. And in fact, what Pearson's does, it's nothing more than the Pearson's correlation between the ranking of the 2 variables. So the way it's implemented, we simply take the ranking of the data, and then we do Pearson's correlation. And what this implementation will give you, it will give you, again, a p-value and the coefficient, which in the case of Spearman is called rho, the Greek letter, and not r. OK, so I think maybe now is a good time for a quick demonstration of using all of those different tests which we've seen.